Welcome back to Discovering Geometry with Mrs. Becky Berry. This is Lesson 69, the start of Chapter 12. Today we will be talking about trigonometry. Trigonometry is the study of the relationship between the sides and the angles of triangles, specifically right triangles. Trigonometry has its origins from astronomy over 2,000 years ago, as astronomers calculated and predicted paths of planets and stars based on triangle angles and circular orbits. Early mathematicians discovered that when the ratios of right triangle legs were close to a certain fraction, the opposite angle was close to a certain measure. Today we will study these ratios. But first, we need to name the sides of the triangle so that we can consistently talk about the ratios. On a right triangle, the side across from the right angle is always called the hypotenuse. Right here we have the hypotenuse. It is opposite of the right angle. Then we refer to the reference angle, right here. In this picture we've labeled it theta. The leg next to the reference angle is the adjacent leg. The leg opposite of the reference angle is called the opposite leg. It makes no difference how we draw the right triangle. Here's the one that we just had, but we can draw it in a different direction, and we would still have the leg opposite of the reference angle as the opposite leg, and the leg next to the reference angle as the adjacent, and the hypotenuse is always opposite the right angle. In the same triangle, we can change where the reference angle is. Here it was down in the left side, and now we have it up at the top. Now that we have it up at the top, the leg next to the reference angle is the adjacent angle. Notice that if you were to measure these two triangles, the opposite leg in this top triangle would be the same measure as the adjacent leg in this one. Because we have used a different reference angle, we now switch the opposite and adjacent legs. So let's look at the possible ratios. There's three possible ratios from the three sides of the triangle. We can compare the opposite to the hypotenuse, the adjacent side to the hypotenuse, or the opposite side to the adjacent side. We call these three ratios sine, cosine, and tangent. We will abbreviate them most of the time as SIN for sine, COS for cosine, and TAN for tangent. Let's look at how these ratios compare. Sine is the comparison of the opposite to the hypotenuse. Remember that the opposite will always go on top and the hypotenuse will go on the bottom. Cosine is the comparison of adjacent to the hypotenuse with adjacent on top of the fraction and hypotenuse on the bottom. Tangent is the comparison of the opposite side over the adjacent side. Sine, opposite, and hypotenuse is SOH. Some people like to say so, ka, toa. If you stub your toe really hard, you might so, ka, your toa. Other people have other mnemonic devices to memorize these. It's very important that you know these right away. So if you don't remember so, ka, and toa, then you need to maybe look up a mnemonic device that you can remember to help you remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. We will be using these the rest of this chapter, and as you continue on through math, you will need to know these right away. This is something that you will memorize and hopefully know the rest of your life if you do math. We use the side lengths in the ratio to find a number. We can express that number as a fraction or as a decimal. That number corresponds to an angle measurement. When trigonometry was first used, there were charts of these ratios and corresponding angles, like the picture below. Now we often just use a calculator to give us the ratio or the angle measurement, depending on what we're looking for. So if you put the opposite over the hypotenuse and you find that that fraction corresponded to the decimal 0.1045, you would come down and look. Sine was opposite over hypotenuse. Your fraction turned out to be 0.1045. That means that your angle would be 6 degrees. Maybe you have an angle of 10 degrees, then you would know that the side length ratio should be 0.1736 for the opposite over hypotenuse. So you can use the table both directions. We're now going to do an investigation. We're going to make a trigonometric table with one triangle. We're going to use our protractor to make a large right angle where measure A is 20 degrees, measure B is 90 degrees, and measure C is 70 degrees. Then I want you to measure the lengths of the sides of your triangle, AB, AC, and BC, to the nearest millimeter. We want a couple decimal places there so that we can accurately describe these ratios. You will then use your side lengths and the definitions of sine, cosine, and tangent, definitions meaning opposite over hypotenuse or adjacent over hypotenuse, to complete this table. Round your calculations to the nearest thousandth when you're getting your decimals. You will then calculate the average of each ratio. If you have partners or group to do this with, you're going to do the average of all of your partners or group. If you don't have anybody to work with, then draw another triangle and just average the two together for your ratios of sine, cosine, and tangent at 20 degrees, and then turning your triangle, doing sine, cosine, and tangent of 70 degrees. Then you're going to analyze your results. What observations can you make about the ratios you found? Is there a relationship between the values of 20 degrees and the values for 70 degrees? You should be able to find some relationships that exist. Then you're going to experiment with your calculator, determine how you find sine, cosine, and tangent. I want to caution you that most calculators can change between putting in degrees or putting in radians. Somewhere on your calculator, you should have a menu option or maybe a button that changes between degrees, DEG, and radians, RAD. Most of the time on my small scientific calculator, it will be showing up at the top all the time if I am in DEG or RAD. Because these measurements are in degrees, we want to make sure that our calculator is in DEG mode. Then use your calculator to find what you just found by calculating the side lengths. Put in sine of 20, put in cosine of 20, put in tangent of 20. Do those ratios match your table? Here's my 20, 70, 90 triangle. Then I measure the sides and I have a short side of 6.04, the hypotenuse of 17.66, and my longer side is 16.6. For my sine ratio of 20 degrees, my sine is opposite over hypotenuse. So I'm going to put 6.04 divided by 17.6. And I found that that fraction became the decimal 0.342. So then for cosine, I'm going to do my adjacent. That'd be 16.6 over 17.66. And that comes out to be about 0.939. Then my tangent will be opposite over adjacent. So 6.04 divided by 16.6. And that comes out to be about 0.364. Now, when I go over to my 70-degree angle, the opposite and the adjacent switch numbers, right? Because the names switch because I've moved over, so my adjacent is now this close one. Sine would then be 16.6 over 17.66. That would be 0.939. And then cosine would be adjacent over hypotenuse. So 0.342. My tangent is now opposite 16.6 over 16.04. So that is 2.748. Do you right now see some similarities? Can you compare how these are? Well, when we did sine of 20, we did the 6.04 over 17.6. When we did 70, when did we have 6.04 over 17.66? Well, it's the adjacent side, so we had it at cosine. So you'll always find in a triangle that the sine of one angle will be the same as the cosine of the other. And the sine of this angle the same as the cosine here. How did the tangents compare? You may not see it, but if we think about the fraction, for 20, we had 6.04 over 16.6. For 70, we had 16.6 over 6.04. So those two are going to be reciprocals of each other. You're just flipping that fraction. Now let's get to some examples. At a distance of 36 meters from a tree, the angle from the ground to the top of the tree is 31 degrees. Find the height of the tree. So we are given the distance, we've given this triangle. The distance away is 36 meters, and this angle here is 31. If we're looking at the height of the tree, we want the opposite side to 31. So here's our triangle again, just the triangle without the picture. What sides of the triangle are we looking at? Well, with this reference angle of 31 degrees, we have the adjacent and we want the opposite side. That would be the height of the tree. What trig ratio uses the adjacent and the opposite sides? TOA. Tangent uses opposite over adjacent. So now we're going to put in what we already have. We know the angle measurement of 31 degrees, so we're putting 31 degrees in. We do not know the opposite side, but we do know the adjacent side. So the adjacent side is 36 meters. So we have an x here for the opposite side. Now we're going to solve for our unknown. Our unknown is the x at the top. I could start by just putting tangent of 31 in my calculator, but I'm going to solve for x first. To get x by itself on this side of the equation, I'm going to multiply by the 36 meters. So these cancel. Now I have x is equal to 36 meters times tangent of 31. That's much easier to put it all into my calculator at once to get my answer. So I get that x is 21.6 meters. Looking at my triangle, does that make sense? This leg was a little bit longer, so 21 for this leg does make sense. Example 2. Find the length of the hypotenuse of a right triangle if an acute angle measures 20 degrees and the side opposite the angle measures 410 feet. We're going to need to draw our triangle to figure out what we want to find. Here's our triangle. We can put either of these as our 20 degrees. I'm going to choose this one up here. So now I've put in my 20 degrees, so the opposite is going to be 410 feet. Now we have the angle and the opposite side, and we need to find the hypotenuse. Which ratio will we be using when we have the opposite and the hypotenuse? It'll be sine. We're going to set up this ratio. Sine of 20 degrees is the opposite over the hypotenuse. Opposite is 410 feet, and our opposite, our hypotenuse is what we don't know. So now we want to solve for this. Remember last time I said that I like to set everything up as x equals and then put it in my calculator. So right now I have sine of 20 is 410 feet over x. Now if I rearrange this and I multiply both sides by x, now I have x sine of 20 equals 410. If I divide by the sine of 20, I will have x by itself. So now I have that x equals 410 divided by sine of 20. So if you're working with just a scientific calculator, this will work out really well. 410 divided by sine of 20 degrees. You should find that x is, I'm going to round just a little bit, so 1,198.8 feet. Now that's a really big number to compare to 410. Does that make sense? Think about if this is 20, this would be 70 degrees. Now we might not have drawn our triangle correctly, or in the right proportions, because 20 is going to be really small and 70 is going to be pretty big. That means that across from the 20 should be a short side, and across from the 70 should be much longer. So this does make sense. 1,198.8 feet is going to be much longer than the 410 because 70 is going to be much bigger than the 20 degrees. Always at the end of your problems, think about, does that make sense? You may not have drawn your triangle to the right proportions, but at the end you can compare, the smallest angle and the smallest side. If they're opposite each other, then you're probably doing it right. Example 3, find the perimeter of this quadrilateral. Now, when we first look at it, we do not know if it's a rectangle or just a quadrilateral, but let's look a little closer. They give us that these are 90 degrees and that these sides are the same. And then this side is going to be the same for each of these two triangles. We're given the 35 degrees. I think that we can safely say that we have an angle, we have a right triangle, and a same side leg and the same side hypotenuse, that these triangles are going to be congruent. That means that these opposite sides would be the same. It also means that this is going to be a rectangle. So let's put in what we know. If we have 35 here, then I know that this one is also going to be 35. And that this side will be congruent to this side. So now we are looking at a rectangle. If I'm just talking about this triangle up here and I want to find this top side, I have an angle and I have the hypotenuse and I'm looking for the opposite side. So what do I use to find that? That's right, I'm going to use sine. So sine of 35 degrees is my x that I don't know over my hypotenuse of 85 meters. So remember to set this up in our calculator, put in 85 meters times sine of 35 degrees, and we'll get what x is equal to. We'll say 48.75, and we can go ahead and label it in meters. The sine of 35 degrees, that ratio, that decimal, has no units. So if I multiply no units number times 85 meters, then my units are going to be meters. Now over here, I might label this side y. How can I find y? Well, again, I have the 35 degrees. I have 85 for my hypotenuse. Y will be adjacent to my 35 degrees. So cosine of 35 degrees would be my adjacent side over my hypotenuse. Same way in my calculator, I'll put cosine of 35 degrees times 85 meters, and y is about 69.63. Now my perimeter is going to be x plus y plus x plus y. Or I could say it's 2x plus 2y. Two times 48.75 plus 2 times 69.63. All of this is in meters. And the end, I'm going to round to just the tenths, 236.8 meters for the perimeter of this quadrilateral. Last example today, find this angle, tangent of x, meaning I don't know what my angle is. That ratio is 48 over 106. When I'm trying to find what the angle is, in my calculator, I'm going to use the inverse function of tangent. So it usually looks like this in your calculator. And instead of putting the angle in here, you'll put the ratio. And this will give you x. And again, if your calculator's in DEG mode, it will give you x in degrees. It's called inverse tangent when we say it out loud. Inverse tangent of 48 over 106 will give me that x in degrees. Let me show you what it looks like on your calculator. If you have a scientific calculator like this, you're going to be using, it's right here, sine, cosine, and tangent, but above it, you should see a sine -1, a cosine -1. So you'll push the second button and then tangent in this case. So second tangent would give you the inverse tangent. It should then come up on your screen as tangent to the -1 and open parentheses, and you'll put in your 48 over 106. You should have x coming out to about 24.36 degrees. Make sure you know how to use your calculator correctly with sine, cosine, and tangent, and also inverse sine, cosine, and tangent to go in the opposite direction.